You are listening to another wonderful episode of Space Nuts, and I am your host for today, Heidi Campo. Well, our beloved Andrew Dunkley is out on holiday. Don't worry, he will be back soon, but the brains and brawn of the show, your beloved Fred Watson, is here with us today. Fred, hello.
Hello, Heidi.
You ready to answer some questions on our Q&A episode today?
Yeah. Look, Q&A is the real meat of Space Nuts because we love people telling us what they want to hear about. It's far better than me spouting on things that they don't want to hear about. So, yeah, sounds ready to go, all ready to go.
We get just such a wonderful, diverse range of questions from our listeners. Starting, today, we have Thomas. Dear Professor Fred Watson, my name is Thomas Wood. I'm a year 11 student doing my research project on the question, and the question that I have is, what is the chance of a habitable planet being found, here's the key word, within our lifetime? So what do you think, Fred, within our lifetime?
Yeah, we're talking here about planets of other stars, exoplanets. It doesn't really matter whether they're habitable or not because they're so far away. We're never going to manage to get to them within what you might call a human timescale. But there are certainly candidates already for habitable planets. Among the 5,000 or 6,000 exoplanets that we know of today, and there are more being discovered all the time, there are planets that sit within the habitable zone of their parent star, and may have atmospheres that could sustain life. Those have not yet been confirmed. They've not been definitively confirmed, but I do think they will be within our lifetime. And probably, Thomas, as a year 11 student, your lifetime is rather longer than mine is, but that's all right. I can deal with that. I think we'll find them within my lifetime. There you go. That's putting the odds on it.
Well, Fred, I think you have certainly done a lot with your lifetime so far, and you have really broken the ground for so many more to follow. Our next question is an audio question. This is Adriano from Florence, Italy.
Hi, Fred and Andrew. This is Adriano from Florence in Italy. I was listening to a conversation about Ligo, so the laser interferometer, where they explain that by measuring the gravitational waves from two colliding black holes, for example, they can also estimate the mass of the two objects. Can you please explain how they can do that? And they also mentioned that with a much more sensible instrument, we should be able to measure the gravitational waves from the Big Bang. Is this correct? And if so, will we be able to estimate the mass of the entire universe and therefore to confirm or deny the hypothesis around the dark energy and dark matter? Thank you guys for your inspiring podcast. Bye-bye.
These are fantastic questions from Adriano, really, on the edge of our knowledge, really. And it's a good question. So LIGO, as you said, the Laser Interferometer Gravitational Wave Observatory, is one of several gravitational wave observatories now. LIGO was the first to actually detect gravitational waves back in 2015. And what we saw was, gravitational waves are formed by vibrations in space, and waves move through space, which, they're basically propagated by the vibrations. The waves are propagated by the vibrations of space because space is flexible. It's 100 billion times more rigid than steel, but it's still flexible. So what we have is this phenomenon where we can actually measure those vibrations directly. And it turns out that LIGO is sensitive to gravitational waves with the same sort of frequency as the audio waves that we hear through our ears. So audio waves are frequencies of a few hundred kilohertz, and the gravitational waves that LIGO is sensitive to are the same. And when you look at the traces of these waves, you can see them in great detail, and measure the way they change as two black holes or neutron stars combine together, because there's a characteristic signal. It's called the chirp. I'll do one for you, Heidi, because I haven't chirped to you before. If you listen to the audio, it sounds like, and the chirp at the end is when the the black holes actually merge. They come together. And it's the way that signal changes over those few tens of seconds at the end of their lives that let you model exactly what it is that is coming together. You can model the objects that are colliding by analyzing that waveform in detail. So that's how it's done. You don't look as though you believe me there, Heidi.
I just think Adriana's question was a little bit over my IQ, or at least my knowledge base. But this sounds very fantastic, and I'm very excited for all the people who understood Fred's explanation.
Let's go to just finish off his other question, though, because that's really interesting. He says, with a bigger interferometer, could you detect the Big Bang? And the answer is basically no. You need something quite different. So, as I said, the LIGO and its ilk are sensitive to gravitational waves with kilohertz frequencies. So a few hundred cycles per second, as we used to call it. Did I say kilohertz? Yes, I meant the wrong.
Yeah.
I'm talking. Yeah, kilohertz are a bit high. It's hundreds of hertz rather than kilohertz. So, 500, 600 hertz. Kilohertz is 1,000, obviously. So just replay that bit. Anyway, the bottom line is to look for phenomena in the early universe. And it's not so much the Big Bang itself as the inflationary period that followed it, when the universe expanded by 10 to the power 50 and 10 to the minus 33 of a second, which is just beggars the imagination. But to pick up phenomena like that, you need to be sensitive to gravitational waves with nanohertz frequencies. That means, how can I put it? A billionth of a cycle per second. In other words, they make one cycle over a very long period of time, years, decades, maybe even millions of years with some of them. So you never see the vibrations. You just see part of one cycle because it's so slow. The period of these vibrations is so slow. And so you need different technologies to do that. And people are working on those. And indeed, we've spoken about some on Space Nuts in the past.
People just like you. I'd say people like you and me, but probably a little bit more people like you.
Let's take a short break from Space Nuts to tell you about our sponsor, NordVPN. Now, I've talked about virtual private networks before and how they can protect you online, and no one does it better than Nord. Now, I've been using Nord for over 2 years and I have no complaints. I'm also using some of their other tools, including the brilliant password manager and the 1 terabyte of cloud storage. And let's face it, you just can't get enough storage these days. And cloud storage is good because it's backed up. If you've got it on a drive attached to your computer, that drive will eventually die and you don't want to lose all that stuff. Cloud storage is the way to go. Right now, Space Nuts listeners get an exclusive deal, 4 months extra for free when you sign up for a 2-year plan. And that's a saving of 74%. Plus, it comes with their 30-day money-back guarantee. All you have to do is head over to NordVPN/SpaceNuts and click on Get NordVPN. You'll see all the current deals and options, including their VPN service, malware protection, ad blocker, tracker blocker, their awesome password manager, and even a data breach scanner. Seriously, have a look at it. NordVPN.com/SpaceNuts. NordVPN.com/SpaceNuts. All right, let's get back to the show.
0G, and I feel fine.
Space Nuts.
Our next question is actually from your side of the world, and it's from Anthony. Anthony, love the show, of course. My question is Even though the moon's orbit is tilted relative to the Earth only by only 7 degrees, why does it appear to shift so much in the sky? Tonight, for example, it is really low in the north from my location in Sydney, but at other times, sometimes not too far apart, it is almost overhead. It must be simple geometry, but the differences seem far too great to be 7 or 14 degrees. It seems like much more than 45 degrees, certainly more than the first 3 lengths. Thanks. And that's from Anthony from Sydney, Australia.
Yeah, he's probably not very far from where I'm sitting now. Hello, Anthony. So
7 to 14 degrees away from you.
Yes, it could be. So actually it's 5 degrees, not 7 degrees. The tilt of the moon's orbit is 5 degrees. But the main point is that its tilt, that 5 degrees, is with respect to the ecliptic, which is the plane of the Earth's orbit in space. So, and in the sky, the ecliptic is the path of the sun through the sky. So 5 degree tilt to the ecliptic means that effectively the moon follows the sun's path through the sky with a bit of 5 degrees either side of it. So that as Anthony says, that's not very much. But the bottom line is, of course, the sun's path through the sky is tilted at 23.5 degrees with respect to the equator. And that's why we see such large variations. So if you think about what the sun does in a year, the moon does more or less the same thing in a month because it goes around the ecliptic 5 degrees one side or the other of it, but more or less going around the ecliptic in 1 month, which is why over very short periods of time, you see the moon in very, very different places in the sky. One little characteristic, and this might illuminate one of the comments that Anthony made, is that when you're near the solstices, either the summer solstice, which for us in Australia is in December, the sun is at its highest in the sky, or the winter solstice, which for us in Australia is June, then the moon in its path through the sky, basically, when it's full, a full moon is exactly opposite where the sun is. So when the sun's very high in the sky, a full moon is very low in the sky. It's right opposite it, within 5 degrees either side. So I always think of that when I look at a full moon. I imagine it's where the sun will be in 6 months' time at the different time of year, which is kind of quite cute, really, in a peculiar sort of way. So yes, it's a good observation, but the reason for it is, as you said, it's geometry.
I never thought of that. That's a quite a cool little tidbit. I'm thinking back. This is a little bit of a side story, but I got married. I told my husband I wanted to do an astronomy kind of themed wedding. And so we got married we chose the October full moon, the hunter's moon. And we got married, and then we immediately, the next day, we were driving across the country because I was from Utah. He was in Florida at the time. So we started our road trip to Florida the day after we got married. And I just remember, because we did our full moon wedding, and I got married right at the time that the moon was supposed to be at its fullest. I'm a little bit of a weirdo. But then the next day, the moon was so low in the sky and bright red. I just remember it was the most brilliant looking thing I've ever seen. And so just really kind of thinking about Anthony's question with, when we got married, it was up in the sky, and then the very next day it's right down low on the horizon, like a movie. It was like almost like a Lawrence of Arabia type kind of look. It was very cool.
Heidi, I'm going to pick up on that today because I can't resist this. Marnie and I too had an astronomical wedding. We got married, and this is why I'm picking up on this. 6 years ago today. It's actually today is our anniversary.
Oh, happy anniversary.
Yeah, thank you very much. Yeah, we've been together for nearly 20 years, but it took us quite a while to get married. 6 years ago today, we got married on the summit of Haleakala on Maui, which has a number of large, significant telescopes on it, including Pan-STARRS 2, the Asteroid Guardian Telescope, and the Daniel K. Inouye Solar Telescope, which is the biggest solar telescope in the world. They were right behind us when we got married at 10,000 feet on the summit of Maui, and I got wonderfully sunburned on the top of my head.
Oh, that's such a beautiful story. Well, congrats to you,
Thank
and
you.
congrats to yours. And that's such a beautiful story. I guess we're dedicating this episode to our significant others and the
Indeed,
moon.
that's right. Yeah, and the moon. That's right. Yeah. sorry to hijack that conversation.
Oh no, that was a fun. Maybe people are curious about your your personal experiences with space, because I think sometimes it's nice to infuse a little bit of the personal love for space too.
Okay, we checked all 4 systems and keying was a go.
Space Nuts.
Our next question is an audio question, and this is Mikey from Illinois, USA.
Hey, Fred and Andrew. This is Mikey once again from Illinois in the U.S. of A. I'm just wondering if you guys have any room in your house for me and my family. I'm just kidding. Unless you're serious. I'm just joking. Unless you want me to. I'm just kidding. Keep it in mind. So I know that space can bend, space can warp, space can ripple, space can supposedly tear. I was curious as to what it means for space to actually tear. Like, have we seen examples in real life of space tearing, and what would that look like? Or is it just we know it can, but we haven't seen it? I was just hoping you guys could explain that a little bit more. Appreciate you guys. Love the show.
What an interesting question. And it is hypothetical, the idea of space tearing, because we've never, ever seen anything symptomatic of tearing space, either here on our planet or in the wider universe. And it would have to be under very, very extreme circumstances that it would happen. By extreme, I mean space being stretched beyond its limits. And the reason why this is a popular notion is because of the discovery back in 1998 that space is accelerating in its expansion. We've known since 1929 that the universe is expanding. That's taking space with it. But since 1998, we've known that expansion has been ever faster, ever more rapid. It's accelerating. And so that's given rise to the idea of, if this goes on into the far distant future, are we going to get to a situation where space is so stretched that it falls apart? And that gives rise to the notion of the Big Rip. And actually, the best place I can direct Mikey to on the web, because it's explained very, I won't say concisely, it's explored in great detail, but it's quite easy to read, is the Big Rip entry on Wikipedia. I'm a big fan of Wikipedia, and the Big Rip entry is really quite extraordinary because it talks about the hypothesis that space could tear. It talks a little bit about the work that's been done on this, the research that has been carried out in a serious, academic manner as to what might constitute space being ripped apart, and you can sort of define that in terms of the various fundamental forces of nature, and there is a hypothesis that then suggests what might be the trigger for a big rip in terms of, the tension that is involved. And that one of the authors of that hypothesis is Robert Caldwell of Dartmouth College, who presents us with a formula which defines when the big rip will take place. It's quite a neat formula. It includes things like the Hubble constant and the baryonic mass content of the universe. It's all there on the page. And I think the bottom line is it 20 billion years? I think something like that. Oh, no, wait a minute. The earliest is 152 billion years' time. That's when space will tear.
So we've got time.
Yeah, 152 billion years. Put it in your diary, Mikey, because that's when you will find the first example of space being ripped.
Oh my. Well, our very last question is from my side of the world again. So we got Greg from Minnesota. So he says, hello from Minnesota, USA. I'm Greg, and I have a question about the cosmic jerk. And no, I don't mean Fred. Oh, Fred. And his question is, the change of position over time is velocity, and the change of velocity over time is acceleration. But we don't need to stop there. The change of acceleration over time is called jerk. We know the universe is accelerating, but have we been able to measure whether or not it's accelerating at a constant rate? Love the podcast. Keep up the good work. If you're curious, the next derivatives after jerk are snap, crackle, and pop.
Yeah. So I'll refrain from using the term jerk since it's been applied to me, and give it its proper name, which is the rate of change of acceleration. So acceleration is the rate of change of velocity. Velocity is the rate of change of position, exactly as Greg says.
I was thinking this question was going to be for me for a second. I was like, wait a second, that's what I do my research in.
Yes. So yeah. But Greg's question is very, very topical at the moment because, yes, we've known that the universe is accelerating, as I said a few minutes ago, since 1998, discovery made by an Australian and a US scientist working independently. That discovery immediately led to the question, is the acceleration changing? In other words, is there a rate of change of acceleration? And that's a very hard observation to make. You need to look at the universe over the widest possible range of look-back times. So you want to look back 11 billion years if you can, sort of 7/8 of the age of the universe. And so what's happened recently is something called DESI, which is the Dark Energy Survey Instrument. And dark energy is, by the way, the mechanism which we think is causing the universe to expand, that space has an energy of its own. Until now, we've believed that was a constant, that the acceleration of the universe was a constant. But DESI, the Dark Energy Survey Instrument, on a telescope in Arizona, based on the Mail telescope, the 4-meter telescope at Kitt Peak, that seems to be indicating, and it's still not speculative, it's still one of these results that's still got a question mark over it, but it seems to indicate that the acceleration is slowing down. And slowing down the acceleration is a good thing, because it might put off the big rip beyond 152 billion years, might push it back into the more distant horizon. So it remains to be seen, but I think the odds are that over the next few years we'll find compelling evidence that the acceleration of the universe's expansion is slowing down. And that's a mystery because that needs a mechanism. And it probably suggests there are new physics that we do not understand that have yet to be determined. And it opens up all kinds of areas of research, which seems like a really good way to wrap up this Q&A session of Space Nuts.
Absolutely. I'll tie that in with love, another one of life's greatest mysteries, since we're talking about our loved ones. If there is somebody that you love and you would love to share this podcast with, we would be just tickled if you could tell everybody that you love, and maybe some people that you don't even really care for, but you just sit next to them at the office. Tell your friends, tell your family, tell the people you don't like, tell your dog, tell your cat about Space Nuts. We are here for you. We've got our question and answer episodes and our more, what do we call it? More narrative story style episodes every week. And so, Fred, do you have anything else you want to add before we sign off for the day?
I think we've covered so much of the big mysteries today that we should just go away with our heads spinning and try and think of some more questions for next time.
Excellent. Well, hey, Fred, thank you so much. This has been another episode of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.